Hello everyone, welcome to Technical Intercepts. This video is all about oscillators. So let's start. An oscillator is an electronic circuit that produces a periodic continuous oscillating signal which can have a wide range of wave shapes and frequencies that can be complicated or just often a simple sine wave or a square wave. Oscillators basically convert a unidirectional direct current DC from a power supply to an alternating current AC. We can find oscillators in many electronic devices like clock generators, digital instruments like calculators, computers and peripherals. Most found examples of signals generated by oscillators are from signals broadcasted from radio transmitter, television transmitters, signals from electronic beeper and quartz clock, which is the internal hardware of computer. An oscillator is principally an amplifier with a positive feedback or regenerative feedback. Regenerative because the output is regenerated with no input because of the continuous amplification of the electronic noise which was present in the open loop amplifier. Feedback amplifier sometimes behaves as oscillators because they usually surpass the losses of their feedback resonator, which is made of capacitor, inductor, resistor in the form of capacitive reactances, inductive reactances by applying a DC supply voltage to that feedback resonator. To be very brief, an oscillator generates oscillating output but without any external input. The conditions for an electronic device to be an oscillator: first condition, it must satisfy the Barkhausen criterion, and the Barkhausen criterion states that the total phase angle around a loop as the signal proceeds from input through the amplifier, through the feedback network and back to the input again, completing a loop, is precisely 0 degrees or 360 degrees. Second condition, the magnitude of loop gain must be equal to 1 or unity. But practically, oscillation starts only when the magnitude of loop gain is greater than 1. Magnitude of loop gain must return to unity. If it remains greater than 1, then we will get overdamped oscillation. And if it returns to unity, then we will get sustained oscillation. In oscillator, the gain of that feedback resonator beta should be less than 1. And the gain of the open loop amplifier, that is basic amplifier, should be greater than 1. When the output from the open loop amplifier is fed to the feedback resonator, the phase angle of the feedback resonator will vary as the function of frequency of the signal incoming to it. This phase change happens because of the reactive elements present in the feedback resonator, that is capacitor and inductor. And this phase change between voltage and current is called as in phase when the phase angle between V and I is 0 or 360 degrees, and this will happen at resonant frequency when both capacitor and inductor are tuned. And at tuning of capacitor and inductor, both the reactances of capacitor and inductor gets cancelled out or coincides, and here only the DC resistance is left. The phase change between voltage and current is called as out of phase when the phase angle between V and I is some theta degrees, and when V leads I, this happens only when inductive elements are left in feedback resonator, making capacitor as open circuited and making the reactance of capacitance very high. This happens when the input signal to the feedback resonator is of low frequency. And when I leads V, this happens when only the capacitor element is left in the feedback resonator, making inductor as open circuited and making the reactance of inductor as very high, and this happens when the incoming signal to the feedback resonator is of high frequency. All this phase change is called the phase shift, and the formula for phase shift is phi equal to tan inverse XL minus XC by R, where XL and XC are reactances. The feedback resonator will add up an extra 180 degree phase shift to the incoming signal, thus by inverting its original direction and by maintaining basic amplifier gain greater than 1 and the feedback resonator gain beta less than 1, we can achieve sustained oscillations. There are basically two types of oscillators: sinusoidal oscillators, also called as harmonic oscillators, and non-sinusoidal oscillators, also called as relaxation oscillators. Sinusoidal oscillator generally generates a purely sinusoidal waveform which is of constant amplitude and frequency, whereas non-sinusoidal oscillators generates complex non-sinusoidal waveform that varies very quickly from one condition of stability to another. Example of non-sinusoidal oscillators are square wave, triangular, sawtooth, and train of pulses. Oscillator resonance is a condition in an oscillator that happens when a constant amplitude and a time or frequency varying signal is fed to the feedback resonator, and the reactive elements that are present in the feedback resonator will respond to that frequency varying incoming signal. At high frequency, the capacitor is short circuited and is connected directly to that incoming signal, and the reactance of capacitor is very low, whereas the inductor is open circuited and is disconnected from the circuit, and the reactance of inductor is very high. The capacitor stores energy in it in the form of electrostatic field at high frequencies. At low frequency, the capacitor is open circuited and is disconnected from the circuit, and the reactance of capacitor is very high, whereas the reactance of inductor is very low and is short circuited and is connected to that incoming frequency varying signal. The inductor will store energy in it in the form of electromagnetic field. During high frequencies, the feedback resonator behaves as a circuit having only capacitor as its element, and during low frequencies the feedback resonator will behave as circuit having inductor as its element. Between these two extremes there is a point called the resonant point where the reactances of inductor and capacitor coincides and cancels out each other, leaving only DC resistance behind. These DC resistance will oppose the flow of this frequency varying signal through the feedback resonator, and the phase shift between voltage and current at this point is 0 degrees, that is V and I are in phase. As there is no external DC voltage supplied to this feedback resonator, the capacitor loses its energy to the inductor in the form of electromagnetic field, and the inductor will lose its energy to the capacitor in the form of electrostatic field. During this transfer of energies from capacitor to inductor or from inductor to capacitor, there is an energy loss from the feedback resonator in the form of radiation, or in the form of dielectric loss, or in the form of heat dissipation from the inductor coil. If this loss is not maintained, then we won't get sustained oscillations at the output of oscillator. So to maintain this energy loss, usually this energy which is lost from the feedback resonator is collected and is amplified and is again fed back to that feedback resonator. At resonant frequency point where DC resistance is left behind, if the resistance is very high, then the oscillations are heavily damped in shorter time, or if the resistance is low, then the oscillations are lightly damped with longer time. Oscillation produced by the LC tank circuit, the amplitude of those oscillations decreases at each half cycle and will eventually die away to zero. These type of oscillations are called damped oscillations, and A beta is less than 1 for damped oscillation, and the amount of damping being determined by the quality factor of that circuit. The overall gain of the oscillator must be slightly greater than or equal to 1. If it is less than 1, the oscillations will not start, and if at all it starts, within no time the oscillations will die. And if it is greater than 1, we will get clipped amplitude or a distorted type of oscillation. That's it for this video. Thank you for watching, and don't forget to subscribe.